Chapter 9.1, Sequences and Series. So our goal for this chapter is to use sequence notation to write the terms of sequences. We're going to use factorial notation, use summation notation to write sums, find the sums of series as well. So the definition of a sequence is an infinite sequence is a function whose domain is a set of positive integers. The function values a1, a2, a3, and so forth are the terms of the sequence. When the domain of the function consists of the first n positive integers only, the sequence is a finite sequence. On occasion, it is convenient to begin subscripting a sequence with 0 instead of 1 so that the terms of the sequence become a sub 0, a sub 1, a sub 2, and a sub 3, and so forth. When this is the case, the domain includes 0. Now, the subscripts of a sequence make up the domain of the sequence, and it serves to identify the positions of terms within the sequence. So, for example, A4 is the fourth term of the sequence. AN is the nth term of the sequence. Any variable can be a subscript, for example. I, J, K, and N can also be used. So first, let's just get a little bit of practice of writing the terms of a sequence. So we're going to write the first 4 terms of the sequence given by a sub n equals 3n minus 2. So the first term, a sub 1 equals 3 times 1 minus 2. So it really helps you in figuring out, well, what am I plugging in? So you're plugging in the 1 for n. In this case, we're plugging in 2 for n, 3 for n, and then 4 for n. So therefore, this is 3 minus 2, which is 1, 6 minus 2, which is 4, 9 minus 2, which is 7, and 12 minus 2, which is 10. So letter B, I'm sure you could figure this out as well. So it would be a sub 1 equals 3 plus negative 1 to the first power. A sub 2 is 3 plus negative 1 to the second power. A sub 3 equals 3 plus negative 1 to the third power. And A4 equals 3 plus negative 1 to the fourth power. And so what you're finding here is that this 1, the power here changes the sign, right? That's what the sign is in here. So this first one becomes 3 minus 1, which is 2. This becomes a positive 1, so 3 plus 1, which is 4. And then this is a minus 1 again, which is 2. And this is a positive 1 again, which is 4. And it keeps on repeating. So let's look at a sequence whose terms alternate in sign. So write the first 4 terms of the sequence given by a sub n equals negative 1 to the nth power over 2n plus 1. So we're going to use let's start with a sub 1. So negative 1 to the first power is 2 times 1 plus 1. And then I just like writing it out. So a sub 2 is negative 1 squared, 2 times 2 plus 1. And then a sub 3 is negative 1 to the third power, 2 times 3 plus 1. And then a sub 4 equals negative 1 to the fourth power over 2 times 4 plus 1. So then in the numerator for a sub 1, that's going to be for the first term, is negative 1 over 2 plus 1, which is 3. Then we have a positive 1 over 4 plus 1, which is 5. And then we have a negative 1 over 6 plus 1, which is 7. And then we have a positive 1 over 8 plus 1, which is 9. So notice that the signs alternate. So that's how you get signs to alternate. So if you notice you have a negative, positive, negative, positive, you're going to have something like this in order to help you change the sign. So try this example. Write the first 4 terms of the sequence given by a sub n equals 2 plus negative 1 raised to the nth power over n. Now, it doesn't alternate in sign, at least the final answers do not. But here are the first 4 terms of the sequence if you plugged it in. 1 3/2, 1/3, and 3/4. So we're going to find the nth term of a sequence. Write an expression for the apparent nth term, a sub n, of each sequence. So letter A, we have 1, 3, 5, and 7. So what might be helpful is you say n, okay, is 1, 2, 3, 4, and then it goes all the way to n. And then here are our terms right here, 1, 3, 5, and 7. So we're trying to see how do the n values relate to the terms. And so one way to look at it, like if we don't have a formula, is you just try to kind of figure out the pattern. Now, another way to look at it is that I notice that there is a common difference with this one, so I'm just going to use that. I noticed the common difference here is it's adding by 2 each time, and then I'm going to go ahead and use the formula for this one. So a sub n equals 1 plus n minus 1 times d. So that's for an arithmetic sequence. And so this is an arithmetic sequence here. And so I know the common difference is, this is a sub 1, sorry. The common difference is 2, so d is 2, and the first term is 1. And so one way to figure it out, which I think is a lot nicer, is just to plug in what we have. So 1 plus n minus 1 times 2. And so you get a sub n equals 1 plus 2n minus 2. So we find that a sub n equals 2n minus 1. And so that is the a to the n that we are looking for. Now letter B, so let's write n equals 1, 2, 3, and 4. Now this one does not have a common difference, right? 2 to negative 5, that's 7, negative 5 to 10, with this 10, that doesn't work. If you remember from last year with Algebra 2, we can look at the ratios, and the ratios also don't work, right? It's negative 5 over 2, is that the same as 10 over negative 5? That also doesn't work. So something else is happening here. And so let's try to figure it out by just, looking at the values and how it's changed. So we have 1 and then 2. 2 is 5, 3, 10, and 4, and 17. Now I kind of notice a little pattern here, that if I have 2 squared is 4. 4 plus 1 is 5. 3 squared is 9. 9 plus 1 is 10. 4 squared is 16 plus 1 is 17. Now, if I just think about that in terms of the absolute value of each of the terms, so I'm going to say the absolute value is n is squared plus 1. Okay? Then, what we can write, because we know the signs alternate, and we know it starts with the positive, so we have negative 1 raised to the n plus 1. Because if we plug in 1, 1 plus 1 is 2, and that means it's positive, which is this value here. Then we multiply that by n squared plus 1. So it's a little difficult to try and figure out, and so you just kind of have to try and figure out the pattern on these. So try out these two examples down here, right? The expression for the apparent nth term of each sequence. You could use that arithmetic sequence formula if, for example, you notice there's a common difference here, and then for the other one there isn't one, so you just kind of have to see if you can figure that out. So for the first example, I noticed a common difference of 4, and your first term is 1, so we plugged it in. And so we noticed that the formula you would get is a sub n equals 4n minus 3. And then you plug it in to see if that works, and it is true. For the second example, 2, negative 4, 6, and negative 8, I started with my terms, or I started n is 1, 2, 3, and 4, and I get 2, negative 4, 6, and negative 8. I noticed that each one is just multiplying by 2. The absolute value of it is multiplying by 2, and the signs alternate. So if the signs alternate, I start with the positive. Then I know I have a negative 1 to the n plus 1. So that helps me with changing the sign. Then I'm going to multiply it to 2 times n, right? And if I try it out, 2 times 1 is 2. And then 1 plus 1, that's positive, so that stays. If I plug in 2, 2 times 2 is 4. And then it becomes 2 plus 1, which is a negative, so that gives me a negative 4. So just kind of a couple ways to kind of think about that. It is a little difficult, but see if you can figure out the patterns on the homework when you try these out.